Let's start with our familiar example of a spherical shell of radius r centered on a single point charge q. In our pictorial view of the electric field, the number of field lines leaving this charge is q over epsilon naught. Since all of the lines leave the shell, the net flux out of the shell is q over epsilon naught. Now, if we move the charge inside the shell, the number of field lines leaving the shell, and therefore the net flux out of the shell, does not change. We chose a sphere for simplicity, but this result holds for any surface that encloses the charge. Once we move the charge outside the shell, however, we have a qualitatively different situation. In this case, every field line that enters the shell also leaves the shell. Hence, the net flux out of the shell is zero. Consequently, we see that for the case of the single point charge, the total flux out of the shell is just equal to the charge enclosed by the shell. We'll now move to the more general case of a collection of n point charges. Consider a spherical shell that encloses a subset of these charges. What happens to the flux out of the shell in this case? Here we see charge q1 generating q1 over epsilon naught lines, all of which leave the shell. Charge q2 generates q2 over epsilon naught lines, all of which leave the shell. All charges outside the sphere will generate a net contribution of 0 to the flux, since every line from such a charge that enters the sphere will also leave it. We now have our main result. The total flux out of a closed surface is just proportional to the total charge enclosed by that surface. While this concept may seem somewhat trivial, it is in fact one of the pillars of electromagnetism. Combining the above result with our integral equation for calculating the flux due to an electric field, we obtain what is known as Gauss's law. We'll now work through another example to illustrate how this all works.